Today we're going to do section 1.3, vector equations. A vector is a matrix with only one column. Vectors in Rn, or vectors with n entries, can be written as U with an arrow over it, U with a vector over it, or U underlined. It can also be written as a bold U. For the most part in class, I use U with a vector over it, and this is vector U with n entries. Sometimes in flip charts, you will see it with a bold U. The geometric description in R2, vector x1, x2 is the point x1, x2 in the plane. R2 is the set of all points in the plane. A parallelogram rule for addition of two vectors, so this you should remember from pre-calc or whatever class was equivalent to pre-calc. If u and v are in R2 and are represented as points in the plane, then u plus v corresponds to the fourth vertex of the parallelogram whose other vertices are 0, u, and v. Note that the 0 vector is 0, 0 with the two entries. Let u be 1, 3 and v be 2, 1. Find u plus v graphically and numerically. So let's first go ahead and find this graphically. So if I find u would be 1, 3. So that's to the right 1 and up 3. So vector u would be this vector here. And you always want to label your vectors. So this would be vector, and let me change that to red, u. Then we need to find vector v. Vector v is 2, 1. So we want to label that vector v. And then if I want to find vector u plus v, u plus v would mean I would attach v on the end of this or u on the end of this. So it would be somewhere up here. And this would be u plus v. And let's also do this numerically to see if it looks like this vector. So u plus v, 1 plus 2 equals 3, and 3 plus 1 equals 4. So that would be the vector 3, 4. And if I count that, 1, 2, 3, then 1, 2, 3, 4, it looks about right. Go ahead and try to do example 2 on your own. Let u be 1, 2. Display vectors u, 2u, and negative 3 halves u on the graph. So first start with u, which would be 1, 2. Next we want 2u. U would be 2, 4. And then I need negative 3 halves u. Negative 3 halves u would be negative 3 halves and negative 3. Make sure. So this would be negative 3 halves u. So here, if I was going to find negative 3 halves u algebraically, you would just multiply 1 by negative 3 halves and 2 by negative 3 halves to get 3. And if I did 2u would equal to 4 if you wanted to find it algebraically first or second. Linear combinations. Given vectors v1, v2, all the way to vn in Rn, and given scalars c1, c2, cp, vector y is defined by our constant 1 multiplied by vector v all the way through cp, which is a linear combination. Examples of linear combinations are 3v1 plus 2v2, or 1/3 v1 plus 0v2, and v1 minus v2. There's many different ways, many multiple infinite linear combinations that we could have. Let's look at example 3. Let v1 be 2, 1, v2 be negative 2, 2. Express each of the following as a linear combination of v1 and v2. So I want you to express each of them and also graph them graphically. So if we look at vector A, 0, 3, this would be v1 plus v2. And if I were to actually graph that on here, I'm just going to put it with a point. So 0, 3 would be right here. It would be this vector. And that's where vector A would end. We'll actually draw it on there. And let's look at B, negative 4, 1. Negative 4, 1 would be negative vector 1 plus vector 2, or v1 plus v2. And that would look like that. That would be vector B. Let's look at vector C. C, I could express, it's 6, 6. I could express it as 4v1 plus v2. So 6, 6 would look like that, and that would be my vector C. And the last one, D, I could express as v1 minus 2.5 v2. And vector D would be 7, negative 4. Which would look like that. Let's look at example 4. Let A1 be 1, 0, 3, A2 be 4, 2, 14, and A3 be 3, 6, 10, and B be negative 1, 8, negative 5. We need to determine if vector B is a linear combination of the first 3 vectors. And in order to do that, first let's write this using the definition of a linear combination. So B would equal x1 times a1 plus x2 times a2 plus x3 times a3. Okay, so this is my linear combination. Next, let's write that linear combination as a vector equation. So vector B was -1, 8, -5. And that would equal x1 times vector A, which is 1, 0, 3, plus x2 times vector A2, which is 4, 2, 14, plus x3 times A3, which was 3, 6, 10. This is my vector equation. Next, you want to write the correspondence system. So these are all steps that you need to know how to do, and sometimes we'll have to do. So my correspondence system would be x1 plus 4x2 plus 3x3 equals -1. And then 2x2 plus 6x3 equals 8. And then 3x1 plus 14x2 plus 10x3 equals -5. This is your correspondence system. Now what I want you to do, I want you to try and write your augmented matrix. And I want you to solve for your augmented matrix and then try to write B as a linear combination using your answers from your augmented matrix. So why don't you pause this now and try to do that on your own? My augmented matrix would be 1, 0, 3, 4, 2, 14, 3, 6, 10, -1, 8, -5. What I first can do is I can take half of row 2 and -3 times row 1 and add it to row 3. And that would give me, I'm leaving my first row how it is because it already has that lead in 1. I'm going to take half of row 2. So that would give me my first 1 in column 2. And I'm going to take -3 times row 1 to eliminate that 3 and add it to row 3. And I get 0, 2, 1, -2. Then I'm going to go down here. And my next step, I'm going to take -2 row 2 and add it to row 3 to eliminate this 2. So my row 1 is going to remain the same. My row 2 is going to remain the same. Oops. That would be a 1. And I'm taking -2 times row 2 and adding it to row 3. My next step, I'm going to take 1/5 of row 3, -1/5 of row 3, to eliminate that -5 to get 1, so I'll have a solution for that row. So with this, here, I notice I have 3's for both of these. So I'm going to take negative times row 3 and add it to row 1 and row 2 to eliminate my 3's above so that I have 0's above that 1. So that gives me 1, 4, 0, negative 7, 0, 1, 0, negative 2, and nothing happened to row 3. Then I want to eliminate this 4 above the 1, so I'm going to take negative row 2 and add it to row 1. And I get a 1, 0, 0, 1. And then 0, 1, 0, negative 2. And I was left with 0, 0, 1, 2. So this gives me x1 equals 1, x2 equals negative 2, and x3 equals 2. So B, vector B, is a linear combination of A1, A2, A3, since we can write it like this. So B is a linear combination of x1, x2, and x3. Oops, not x, a's. So A1, A2, and A3. Since I can write B as A1 minus 2A2 plus 2A3. That brings us on to a vector equation. x1 times a1 plus x2 a2 all the way to xn an equals b has the same solution as a linear system whose augmented matrix is a1, a2, an equal b. In particular, vector b can be generated by a linear combination of our a1, a2, all the way to an, if and only if there is a solution to the linear system corresponding to the augmented matrix. So let's look at example 5. Example 5 says, let V equal 3, 4, 5. Label the origin together with V, 2V, and 1.5V on the graph. So if I look at this, we'll actually make it a little bigger again. So here they actually gave us so I'm first going to label V, and this would be V from here to here. Oops. And then 2V and 1.5V. So we'll do 1.5V first. And I'm pretty sure you already know where it is. 1.5V is here. And then 2V. So since they all lie on the same line, so we know that looking at this picture, V, 2V, and 1.5v, all lie on the same line. Span V is the set of all vectors of the form C times V. So C is some constant. And here, span V is a line through the origin. Label U, V, U plus V, and 3U plus V on the graph. So first, I'm going to label U and V for you guys. So this is going to be U. And this will be V. So we need to label U plus V, 3V plus 4V, or 3U plus 4V on the graph below. So let's start with U plus V. U plus V would just be like this. That would be U plus V. And 3U plus 4V, so 3U would be here, plus 4V would be here, so it would go all the way up here. Oops. And what can you tell me about the span of UV? It's a plane through the origin, hopefully you're saying. So we know that U plus V, and 3U plus 4V all lie on the same plane. Span UV is the set of all vectors of the form x1u plus x2v. And here in this picture, span UV is a plane through the origin. The geometric description of span V and span UV. Let V be a non-zero vector in R3. Then span V is the set of all scalar multiples of V, and this can be visualized as the set of all points on the line in R3 through V and 0. If u and v are non-zero vectors in R3, with v not a multiple of u, then span uv is the plane in R3 that contains u, v, and 0. This can be visualized as the plane created by u and v through the origin. Let's look at example 7. Let v1 be 2, 1 and v2 be 4, 2. Find a vector and span v1, v2 and describe the span of v1, v2 geometrically. So there's many different examples you could do here. So I'm going to use my example. So for example, I could have 2v1 plus 3v2. And that would equal 4, 2 plus 12, 6, which is 16, 8. So this would be span v1, v2. Okay. And you would also notice about this, 16, 8, I could multiply v1 by 8 and get 16, 8. I can multiply v2 by 4 and get 16, 8. So span v1, v2 is a line through 0 and v1. Since v2 is a multiple of v1. Example 8, let v1 be 4, 2, 2 and v2 be 6, 3, 3. Is span v1, v2 a line or a plane? So hopefully you notice this here, that it is a line because 1/2 v1 equals 1/3 v2. So span v1, v2 is a line because 1/2 v1 equals 1/3 v2. Example 9. Let A equal 130,215 and B be 8317. Is B in the plane spanned by the columns of A? So what we need to do, we need to determine after I run my augmented matrix if x1 and x2 exist. If they exist, then B is in the plane. If they do not exist, it is not in the plane. Okay, so I know that I could rewrite this as x1 times, because this is like my v1, v2. Okay, so it would be x1 is 130 plus x2 times v2, and that would equal 8317. Then I would take my vector equation and write it as my augmented matrix, and I would go ahead and solve. So going through, there's many different steps you could do. So my first thing that I got is I multiplied row 1 by negative row 3 and added it to row 2 to eliminate this 3 here. And then I'm going to take row 2 and add it to row 3 to eliminate this so it's a 0 as well. And if you notice here, I can't get 0 equals -4. I was hoping to get all zeros here. So because I get 0 equals -4, this is inconsistent. Because you cannot have a solution 0 equals -4. It needs to be 0, 0. So B is not in the plane spanned by columns of A, by the columns of A.